The floor trembles. March 17, 1904, 6:42 a.m., Leeds, England. Inside the Brunswick mill, a machine the size of a railway carriage begins to move. The operator, Thomas Hartley, 43 years old, hands calloused from 15 years in textile work, releases the brake lever. 300 spindles blur into motion. The carriage rolls backward on iron rails. 5 feet, 10 feet, 15 feet, then forward again. Back and forth, back and forth. A mechanical ballet, it will continue uninterrupted for the next 120 years. This is the story of a machine that refused to die. The Leeds spinning mule of 1904 represents something we've forgotten how to build. Permanence. Not planned obsolescence. Not quarterly profits. Not disposable engineering. Permanence. It's a cast iron testament to an age when craftsmen built machines to outlive their grandchildren. When precision meant hand-scraped bearing surfaces and water-cooled gears. When good enough wasn't in the vocabulary. But to understand why this machine matters, we need to go back. Back to the problem it solved. Back to an industry choking on its own limitations. 1780s Britain. Cotton is gold. The demand for cotton thread exceeds supply by a factor of 10. Spinners work 14-hour days, fingers bleeding, producing thread so slowly that weavers sit idle for weeks waiting for material. The bottleneck is human speed, human endurance. Human hands can only twist so much fiber before they fail. James Hargreaves invents the spinning jenny. Multiple spindles on one machine. A leap forward, but the thread is weak. Breaks under tension. Worthless for warp threads. Richard Arkwright develops the water frame. Stronger thread, but requires massive power sources. Water wheels. Limited locations. Enormous capital investment. Samuel Crompton sits in a farmhouse in Bolton. 1779. He's 26 years old, and he's spent 5 years on a problem everyone says is impossible. How do you combine the fine thread quality of the jenny with the strength of the water frame? How do you make a machine that can do what human fingers do, that subtle twisting motion, that precise tension control, but faster? Infinitely faster? His answer: the spinning mule. The name comes from its hybrid nature. Mule, half jenny, half water frame. But the genius is in the carriage. A moving platform that runs on rails, pulling away from the spinning frame as the thread forms, then returning to wind it onto bobbins. The motion mimics human walking while spinning. The ancient craft mechanized. It's crude in Crompton's hands. Wooden construction. Limited spindles. But the principle is revolutionary. By 1904. That principle has evolved into something Crompton would barely recognize. Brunswick Mill. Built 1898. 4 stories of red Lancashire brick. Windows running the entire length north-facing for consistent light. No direct sun to heat the workspace or fade the cotton. The spinning floor occupies 2,000 square feet. 12 mules arranged in rows. Each one 54 feet long. Each one a precision instrument weighing 4 tons. The 1904 Leeds mule is built by Platt Brothers and Company of Oldham. They're the dominant force in textile machinery. Their catalogs read like encyclopedias. Every component optimized through decades of iteration. They've studied bearing friction, gear ratios, tension dynamics, heat dissipation. This machine incorporates 234 separate patents. Thomas Hartley knows every inch of it. He arrives before dawn. Winter morning, frost on the windows. His breath mists in the cold mill air. The boiler room has been heating water since 4 a.m. Steam pressure building in the massive pipe network that powers the line shaft overhead. That shaft, 30 inches in diameter, runs the full length of the mill. When it turns, every belt pulley engages. When those belts engage, 12 mules wake up simultaneously, but Thomas doesn't rush. First, inspection. He walks the length of his mule. 54 feet of mechanical complexity. The headstock at one end houses the main drive wheel 60 inches across. Quarter-ton of cast iron with leather belt grooves machined to tolerances of 1/1000th of an inch. The carriage itself rides on 4 iron wheels, each bearing hand-scraped to eliminate play. 0 slop, 0 wobble. The rails are tool steel, hardened and ground flat to within 2/1000ths across their entire length. 300 spindles stand in formation, each one a tapered steel shaft, 7 inches tall, spinning in brass bearings that were lapped by hand until they could rotate for 5 minutes on a single flick. The brass contains specific ratios of copper, tin, and zinc formulated to be hard enough for durability, soft enough to avoid scoring the steel shafts. Thomas checks the rovings. These are the loosely twisted bundles of cotton fiber that feed each spindle. They come from the carding room downstairs, where other machines have cleaned and aligned the raw cotton fibers. Each roving must have consistent thickness. Any variation will show in the final thread. Any weak spot will snap under tension. He inspects the faller wires, 300 thin metal guides that rise and fall with each carriage cycle, controlling the twist distribution in the forming thread. These wires are phosphor bronze. They flex thousands of times per shift without metal fatigue. The flexibility is precise. Too soft and they flutter. Too stiff and they bind. Everything is lubrication. Oil points every 6 inches. Graphite grease on the carriage wheels. Tallow on the bearing surfaces. The machine consumes 5 gallons of oil per week. But this oil is carefully filtered, carefully applied. A single grain of sand in a bearing can score the journal surface, creating a groove that accelerates wear. In a machine built for permanence, contamination is enemy number 1. 6:30 a.m. The whistle blows. Thomas pulls the engagement lever. The line shaft overhead is already turning, driven by a 250 horsepower steam engine in the basement. His belt drops onto the drive pulley. The main wheel begins to rotate. Gears mesh. The carriage creeps backward, but this isn't simple backward motion. Watch carefully as the carriage pulls away, the spindles accelerate. The rovings unwind from their supply bobbins, passing through the faller wires, feeding onto the spinning spindles. The spindles turn at different speeds depending on their position, the ones nearest the headstock rotating faster than those at the far end. This differential speed creates the twist. More twist near the top, less at the bottom, graded precisely to produce uniform thread strength. The carriage reaches full extension, 4 feet back from starting position. At this moment, the spindles are rotating at 8,000 RPM. The thread formation is complete. Now comes the winding. The carriage reverses. But as it moves forward, the spindles slow. The faller wires descend. The freshly spun thread winds onto bobbins mounted on the spindle shafts. Layer upon layer. Precise traverse. Each wind positioned exactly next to the previous one, with no gaps, no overlaps. The bobbin builds uniformly. The whole cycle takes 45 seconds. 45 seconds to convert 300 rovings into 300 threads. That's 720 cycles per shift. 216,000 threads formed. Each one identical to the last. Each one meeting specifications set by the cotton count, the number of 840-yard hanks per pound. This machine produces 60-count thread, fine enough for quality shirting, strong enough for industrial use. But here's what makes the 1904 Leeds Mule extraordinary. It's still doing this in 2024, not in a museum, not as a demonstration piece cranked by hand once a month for tourists. Actually working, producing actual thread, In the same building where it was installed 120 years ago. How? The answer isn't magic. It's engineering philosophy. When Platt brothers designed this machine, they made choices. Choices that cost more money up front. Choices that reduced short-term profits. Choices that made sense only if you believed the machine would still be running when your great-grandchildren were old. Choice 1. Materials. The frame is cast iron, not stamped steel, not welded construction. Cast iron in sections weighing hundreds of pounds each, poured in sand molds, stress-relieved through controlled cooling, then machined on planers that could hold tolerances across 6-foot spans. Cast iron doesn't fatigue. It doesn't develop stress cracks from vibration. Its dimensionally stable temperature changes don't warp it. And when you machine it properly, it wears in rather than wearing out. The bearing surfaces actually get smoother with use. Choice 2. Bearings. Every rotating shaft rides in bronze bushings. Not ball bearings. Not roller bearings. Bronze bushings that were hand-fitted to each specific shaft. This is slower to manufacture. It requires skilled labor. But bronze bushings, properly lubricated, last indefinitely. They run quieter than ball bearings. They tolerate contamination better. And when they do wear after decades, you simply scrape them again. No replacement parts needed. Choice 3. Gearing. The drivetrain uses cut ears, not stamped ears, not sintered gears. Each tooth profile is generated on a gear cutter, the blank indexed precisely, the cutter fed through at exact depth. The resulting teeth have smooth surfaces and accurate involute profiles. They mesh with minimal backlash, minimal noise, minimal wear. These gears have been running for 120 years, with wear measured in thousandths of an inch. Choice 4. Accessibility. Every component can be serviced without disassembling the entire machine. Want to replace a spindle bearing? Remove 3 screws, lift out the brass bushing, install a new one. Want to adjust belt tension? Turn a hand wheel. Want to change the thread count? Swap one gear for another. They're all standardized sizes, held in place with tapered pins. The engineers who designed this understood that maintenance determines longevity. They made maintenance easy, but materials and design only explain half the story. The other half is Thomas Hartley. And the 5 generations of operators who came after him. Thomas dies in 1947, age 86. His son William takes over the mule. William trains his nephew Robert in the 1960s. Robert trains Margaret Ashworth in 1982, the first woman to operate this specific machine. Margaret trains David Chun in 2001. David is still there in 2024, now training apprentices who weren't born when the internet was invented. Each operator learns the sounds. The healthy whir of properly tensioned belts. The smooth rumble of the carriage wheels on their rails. The high singing note of spindles at full speed. They learn what silence means a broken belt, a jammed gear. They learn what grinding means contamination in a bearing. They learn what clicking means a loose mounting bolt. They learn the oil schedule. Not when the manual says to oil. When the machine says to oil. This bearing needs attention every week. That one goes 6 months. You learn by touching, by feeling temperature, by watching how light reflects off the journal's dry metal looks, different than properly lubricated metal. They learn to read the thread. A properly spun thread has a specific appearance under light. Uniform twist. Consistent diameter. No slubs, no thick spots, no thin spots. If the thread changes, something in the machine has changed. Maybe a faller wire is bent. Maybe a roving is uneven. Maybe the humidity is wrong. Cotton responds to moisture content. The air in this mill is maintained at 65% relative humidity, year-round, because cotton fibers become brittle below 60%. and slack above 70%. This is craft knowledge. It exists in muscles and fingertips and pattern recognition. It cannot be fully written down. Each operator adds to it, refines it, passes it forward, and because of this continuity, the 1904 Leeds mule still runs. The textile industry has moved to Asia. Brunswick Mill now houses a living history museum. But that's a misleading name. This isn't history. This is present tense. The mule runs 2 shifts per week, producing thread that's sold to heritage textile companies, to theatrical costumers, to historical reenactors who need authentic period fabric. David Chun, 62 years old, performs the same inspection Thomas Hartley performed in 1904. Check the rovings. Check the oil levels. Check the belt tension. Listen to the idle machinery. Then pull the lever. The carriage rolls backward. 300 spindles blur. The rovings twist into thread. The cycle completes. Again, again, again. 45 seconds per cycle. 720 cycles per shift. 216,000 threads. The numbers haven't changed, but something has changed. We don't build like this anymore. We've optimized for different values. Quarterly earnings, planned replacement cycles, minimum viable products. We build machines designed to be obsolete in 5 years, replaced in 10, forgotten in 20. The 1904 Leeds mule stands as a reproach to that philosophy. Or perhaps as a reminder. Perhaps as proof that another way is possible. Consider what it represents. 12 decades of continuous operation. 3 generations of war and peace. The rise and fall of the British Empire. The invention of flight, television, computers, the internet. Social revolutions. Economic transformations. Technological upheavals that made entire industries obsolete. And through it all, this machine kept spinning thread. It didn't need software updates. It didn't need firmware patches. It didn't become incompatible with new standards. It just needed oil, adjustment, care, and knowledge passed from hand to hand. There's something almost biological about it. The way knowledge transfers. The way where patterns become data. The way each operator adapts to the machine's quirks, and the machine adapts to the operator's style. It's symbiotic. Human and machine learning each other over decades. You can see this in the carriage rails. They're not perfectly flat anymore. Millions of cycles have worn subtle depressions where the wheels bear most heavily. But the wheels have worn too, conforming to those depressions. The result is actually smoother than new. Metal finding its equilibrium with metal. The system optimizing itself through use. Or look at the main drive wheel. The belt has polished certain areas of the rim more than others areas where tension is highest. Those polished zones are now harder than the rest of the surface, work hardened by friction. The belt itself has been replaced hundreds of times, but each new belt follows the same pattern, creating the same wear, maintaining the same balance. This is adaptation without design. Evolution through operation. The machine becoming more itself with every rotation. Modern manufacturing rejects this. Everything is designed for replacement, not repair. Sealed bearings you can't service. Proprietary parts you can't source. Software locks that prevent modification. We've traded permanence for convenience. We've traded repairability for simplicity. We've traded knowledge for disposability. And maybe that's necessary. Maybe complexity demands it. Maybe scale requires it. Maybe economics proves it inevitable. But standing next to the 1904 Leeds mule, watching the carriage roll backward for the 4 billionth time, you have to wonder what we've lost. Because this machine embodies something we're desperately trying to relearn. Sustainability. Not the marketing kind. The real kind. The kind where you build something once and maintain it forever. The kind where you train people to understand systems, not just replace components. The kind where quality matters more than speed, where durability matters more than cost, where legacy matters more than quarterly targets. The engineers at Platt Brothers understood this in 1904. They understood that the true cost of a machine isn't its purchase price. It's the sum of purchase price plus operating costs plus replacement costs over the machine's lifetime. If you build cheaply and replace frequently, that sum is astronomical. If you build well and maintain properly, that sum approaches the initial investment plus CONSUMABLEs. They chose the second path. They over-engineered deliberately. They used materials that cost more but lasted longer. They designed for access and repair. They created systems that could be understood by skilled operators with hand tools, not specialists with diagnostic computers. And their reward? A machine still running 12 decades later. Still profitable. Still productive. Still teaching. Because that's the other thing the mule does. It teaches. Every apprentice who learns its operation gains something more than job skills. They gain a relationship with materials, with precision, with cause and effect. They learn that proper tension on a belt makes it last 10 times longer. They learn that contamination in oil causes exponential damage. They learn that small problems caught early are trivial to fix, but small problems ignored compound into catastrophic failures. These aren't textile lessons. They're life lessons encoded in iron and brass. This is what we've lost when we lost repair culture. When we made everything disposable, we didn't just create landfills. We eliminated a transmission system for practical wisdom. The knowledge of how things work, how they break, how they heal. You can't learn that from a replacement module. You can only learn it from maintenance, from relationship, from decades of attention. The 1904 Leeds mule is a time capsule, but not in the usual sense. It's not preserving the past. It's preserving a way of thinking about the future. A way that says, build things that outlast you. Pass knowledge to the next generation. Maintain rather than replace. Understand rather than discard. And maybe that's sentimental. Maybe that's nostalgic. Maybe that's economically naive. But that machine is still spinning thread. Still making money. Still functioning after 120 years. Can we say the same about our smartphones? Our cars? Our appliances? Will anything we build today still work in 2144? The question isn't rhetorical. It's diagnostic. It measures the distance between then and now, between a philosophy of permanence and a philosophy of obsolescence, between craftsmanship and consumption, between building to last and building to replace. March 17th, 2024. Exactly 120 years after Thomas Hartley first engaged the drive lever. David Chun stands in the same spot, hand on the same worn brass handle. The floor trembles. The carriage begins to move. 300 spindles blur into motion. Back and forth. Back and forth. A mechanical ballet that shows no sign of ending. This is the Leeds spinning mule of 1904. A machine that refused to die. A testament to engineering philosophy we've forgotten. A reminder that permanence is possible. That quality endures. That the best way to honor the past isn't preservation, it's continuation. The carriage rolls. The spindles spin. The thread forms still. After all these years, still.